By every model we use to understand planets, this one shouldn't still be here. Not in its current state, not after everything that happened to it, and not for as long as it has existed. Planetary systems are governed by limits of heat, limits of pressure, limits of stability. When those limits are crossed, planets change or tail. Atmospheres collapse, surfaces melt, internal structures weaken, energy overwhelms the system. Most worlds that experience conditions like these do not remain intact for long. And yet, this planet does. That contradiction is the real anomaly, because it isn't missing one requirement for survival. It's missing several. It rotates slowly and in the wrong direction. It lost the ability to regulate its climate. It became hotter than any planet should be at its distance. Each of these factors alone would stress a planetary system. Together, they should have pushed it past the point of failure. According to standard models, a planet in this condition should either cool, collapse, or break apart. This one did none of those things. For decades, scientists assumed the explanation had to be incomplete, that something important had been overlooked, that a hidden stabilizing factor was at work, because accepting the alternative was uncomfortable. If this planet truly exists in this state, then the rules we rely on are not as reliable as we think. The models that predict how planets form and evolve are built on probabilities, on averages, on outcomes that happen most of the time. They are excellent at describing what usually occurs, but they struggle when faced with extremes. This planet sits far outside the expected range, not just slightly. Fundamentally, on paper, it shouldn't have survived its early history. The violent formation of the solar system alone should have disrupted it. Later, the loss of atmospheric balance should have accelerated its collapse. Extreme heat should have weakened its structure. Internal processes should have shut down. None of that happened. Instead, the planet persisted. It didn't become stable in the way Earth is stable. It didn't reach balance. It endured. And that distinction matters. Stability implies harmony. Endurance implies resistance. This planet is not in equilibrium. It is locked in a state that should be temporary, but isn't. That forces an uncomfortable question. Is this planet an impossible exception? Because if the planet is real, and it is, then the problem may not be the planet at all. To understand why this planet still exists, we have to stop asking what it lacks. The first instinct was to blame the formation. Early planetary systems are violent places. Objects collide, orbits shift. Energy is released in massive amounts. It seemed reasonable to assume this planet survived simply because it formed differently. Maybe it accumulated mass faster. Maybe it avoided a critical collision. Maybe its internal structure stabilized earlier than expected. For a moment, that explanation worked, until the numbers didn't line up. Simulations showed that even under favorable conditions, the planet should not have retained its current structure for long. Internal heat should have dissipated. The core should have cooled. The system should have relaxed into a more stable state. It didn't. So scientists looked at rotation. Rotation affects internal dynamics. It influences how heat moves inside a planet. It can delay cooling. Perhaps the slow, unusual rotation helped preserve internal energy. Again, this explanation seemed promising, until it wasn't. Models show that slow rotation actually makes planets less stable in the long run. Heat becomes unevenly distributed. Structural stress increases. Instead of protecting the planet, rotation should have accelerated its decline. That avenue closed quickly. Next came the atmosphere. A dense atmosphere can insulate a planet, trap heat, reduce energy loss. Maybe the planet remained hot and intact, simply because it was wrapped in an unusually thick atmospheric layer. Once again, the data disagreed. Atmospheric insulation can explain high temperatures, but it cannot explain long-term structural endurance. Over time, trapped heat weakens materials. It softens the crust. It destabilizes internal layers. A planet insulated for too long should deform, collapse, or change dramatically. This one didn't. One by one, Each explanation failed. Formation didn't account for it. Rotation didn't support it. Atmospheric insulation explained the heat, but not the survival. The models kept reaching the same conclusion. On paper, the planet should not exist in this configuration. This forced a deeper reconsideration. The problem might not be any single factor. It might be the way the models treat planets as systems that seek balance. Most models assume planets evolve toward equilibrium, that extreme states are temporary, that instability resolves itself over time. But this planet never moved toward equilibrium. It moved away from it and stayed there. That behavior doesn't fit neatly into existing frameworks because the models aren't designed to describe endurance under continuous stress. They're designed to describe stability. When a system refuses to stabilize, the math struggles to keep up. This is where the idea of impossibility begins to fall apart, not because the planet defies physics, but because the physics was framed around expectations that don't always apply. The planet didn't follow the most likely path. It followed a survivable one, and that distinction changes everything. To understand why the planet still exists, scientists had to stop asking which rule it broke and start asking how it managed to persist while breaking so many. The answer wasn't hidden in a single variable. It was hidden in the interaction between all of them. The reason this planet still exists is not because it escaped failure. It's because failure didn't arrive all at once. The models we use are built around thresholds, points where systems collapse, moments where change becomes irreversible. But this planet never crossed those thresholds in a single step. Instead, it moved through them slowly. Each change weakened the system, but not enough to destroy it. Each loss made the planet harsher, but still intact. Each extreme pushed it closer to failure without reaching it. The planet didn't survive because it was stable. It survived because it was resilient. That difference matters more than it sounds. Stability assumes balance. Resilience assumes resistance. This planet never returned to balance. It learned how to endure imbalance. Extreme heat didn't shatter it. Atmospheric collapse didn't erase it. Rotational chaos didn't tear it apart. Not because those forces were harmless, but because they arrived in a sequence the planet could withstand. When scientists began reframing the problem this way, the contradiction faded. The planet wasn't an impossible object in a stable universe. It was a possible outcome in a violent one. Our models assume planets move toward calm states over time, but the early universe was not calm, and not every system settles the way we expect. This planet is a reminder that survival doesn't always look like equilibrium. Sometimes it looks like persistence under constant stress. That insight changes how we interpret other worlds. When astronomers observe exoplanets with extreme temperatures, strange rotations, or unstable atmospheres, they often assume those worlds are temporary, that they won't last. This planet suggests otherwise. Some worlds don't fail quickly. They fail slowly, or not at all. And that means the universe may contain far more extreme survivors than we imagine. Planets that exist, not because conditions are ideal, but because they never quite cross the line where destruction becomes unavoidable. This reframes what we mean when we say, a planet shouldn't exist. It doesn't mean physics forbids it. It means our expectations were too narrow. The rules weren't broken. They were incomplete. This planet didn't expose a flaw in nature. It exposed a limitation in how we describe it, and that may be the most important lesson of all. Because if planets like this can exist, then the universe is not just stranger than we thought. It is more tolerant of extremes. Which leads to a final question. If worlds like this can survive, what else might be out there that we haven't learned how to recognize yet? In the next video, we'll look at what this planet teaches us about worlds we haven't discovered, and why some of the most important planets may be the ones that don't look habitable at all.